The next talk and the last talk of the morning will be delivered by Vadim Kaloshin, IST Austria. He will talk about on local spectral rigidity of expanding circle maps.
Thank you very much for the invitation. It's a great pleasure to be here. I actually, the first time I visited IMPA was in the year of 2000, and I had many wonderful interactions with Marcelo since then. It's a great pleasure to be here. So I will. I decided to put a brief summary of my talk. I decided to put a brief summary of my talk on the blackboard because I want to start with the motivation of the problem I'll be talking about, and eventually, probably 10 or 15 minutes into the talk, you will see a model which many people in the audience looked at. So the original motivation is a old problem popularized by Mark Katz, and the problem is, can you hear the shape of a drum? So now I will give you several formulations of this problem coming from different parts of mathematics, and then do you think it's better now? Can you hear me? Without microphone? Is this okay without microphone? But the video will record it. No, okay, I'll just speak a little louder. So the first motivation is come from PDEs, and it does look, to start with, very different. So PD. One. So what you do, you start with a drum head. And what is a drum head? It's mathematically, it's some domain in the plane. And at least those drum heads which I saw, they have a smooth boundary. And the first third of my talk will take place when I have in mind that there is a convex domain with a smooth boundary. And PDE part of the story starts with the Dirichlet problem. And this boundary value problem says that you look at the Laplacian eigenvalue for Laplacian with a zero boundary conditions. And you just record all eigenvalues which are there. And it turns out that there is a lot of structure in the solutions to this boundary value problem, and often it's called Laplace spectrum. It's been a bit more than 100 years ago that Hermann Weyl proved that if you look at the number of lambda j's, which are less or equal than lambda, divide by lambda, and send the limit to infinity, then you will get an area of the domain. So what it tells you that this collection of numbers does know something about the domain. And the classical question by Mark Katz says, does this collection of numbers determines the domain up to isometry? Certainly I need to include isometries, because if you rotate the drum, then it should sound the same. Now let me give you a different formulation of this problem. If the boundary is smooth, the question is wide open. If the boundary is analytic, there are some results by Steve Zeldich. So the second formulation is billiard, and what I would like to do, I would like to play billiard inside of this domain. And playing billiard means that the reflections are elastic, which means that the angle of incidence is equal to angle of reflection. And all I will care about periodic orbits. So what does it mean? So for each periodic orbit, billiard periodic orbit, what I will do, I will look at the perimeter of some associated periodic orbit. I take a union and I take a closure. So for example, if I have a periodic orbit of period 3, then I need to sum all the edges, and this is called the length spectrum. So it also has some symplectic meaning, because if you do area preserving coordinate transformations, then it stays the same. And you could ask exactly the same question for the length spectrum, and the answer is also not known. But what is fascinating is there is a series of work of Shazarian, Gaiman, Melrose, and so on, which basically says the following. It says that if I look at the Laplace spectrum, then it determines the length spectrum. And here there is this little word generically. So somehow, if I record these numbers on this part of the blackboard, then they know the numbers on the other part of the blackboard. And this question definitely looks very dynamical and very appealing. And again, except some special situations being close to a circle and being axisymmetric, the question whether you could determine omega from the length spectrum also stays wide open. But let me go to a third formulation, which is geodesic flows. And for geodesic flows, I want to look at the case when it's on surfaces of negative curvature. And this is a topic which is very popular in dynamical systems. So there will be no boundary value condition, but it is possible to make sense of the first line. So you could define the Laplace spectrum associated to geodesic flow on surfaces of negative curvature. You could certainly define the length spectrum, and this correspondence also stays so you cannot hear it. So for surfaces of negative curvature, let me define marked length spectrum. And what does it mean marked? If I pick a certain homotopy class, then for the corresponding geodesic, closed geodesic gamma, I will keep track not only what is this geodesic, but also where it is coming from. And if I have a different geodesic, say gamma prime, then I will also keep track of the homotopy class it's coming from. So let me define so-called marked length spectrum. And this is a collection of lenses of geodesics. And for each geodesic, I want to keep a label. So H of gamma is a homotopy class, and L of gamma is a lens. And if you have geodesic flow on the surfaces of negative curvature, for each homotopy class there exists a unique geodesic. And then the question becomes, at least motivated by this picture, can you determine your geodesic flow from the Mark length spectrum? And there is an absolutely spectacular result by Jean-Pierre et al. And independently by Kroc. It says that if you look at the Mark length spectrum, then it determines our geodesic flow up to an isometry. So the remarkable part, it's totally non-perturbative. You should not say that your metrics G or G prime are close to each other. And it's all fascinating as a mathematical curiosity, but when you try to solve this equation, there are no labels. So the very natural question to do is, and this is a conjecture by Sarnak, is that does the length spectrum determine SG locally up to isometry. So what I want to do, I want to consider all the lenses of geodesics, and I want to forget about the labels. And I would like to ask myself whether it is possible to reconstruct the corresponding geodesic flow. And this is actually the type of dynamical systems which have been tremendously studied. And what I would like to do, I would like to go down in terms of generality, but I hope some years from now we could approach.
There is a question.
Yes.
So what do you mean by generically over there? Why you...
It's like Kuhn-Cass mail, countably many. It's a bare generic set. You need to assume that all lenses come with multiplicity 1. Eigenvalues are non-degenerate, so it's a countable intersection of open and dense set. And actually, I hope we will soon complete the papers that the exact equality can be violated on a dense set. So, but then I need to define what does it mean. Determines, but generically means all periodic orbits are hyperbolic, perimeters of all periodic orbits are different, and eigenvalues should be away from 1. Could Kuhn-Cass mail tab? Other questions? Okay, so now when you look at geodesic flows on surfaces of negative curvature, one way to look at it is you have conservative ANOSO flow. And at the moment we don't know how to deal with this object, but a slightly less general object which we are slowly putting our hands on is conservative ANOSO maps. And we are really looking at the conservative ANOSO maps from a two-dimensional torus into itself. And parts of the proof which is written shows that there is a potential to do something. But today, what I'm going to talk about expanding circle maps. And Lyapunov spectral rigidity. So we really hope that we will, maybe in a year or two, we will climb the ladder and we will go up. So now let me tell you what kind of rigidity we are studying, and I will formulate the result. So basically, I told you about the first two items. Now let me go to a third item. So, oh, sorry. So, so the setup is the following. I take F is CR smooth expanding circle map. Of degree D. And for each periodic orbit, I define the Lyapunov exponent. And I define the Lyapunov spectrum of F as the union of all Lyapunov exponents over all periodic orbits of period K. So this is my Lyapunov spectrum. So if I take a smooth coordinate change, then the Lyapunov spectrum stays the same. And it does make sense to talk about marked Lyapunov spectrum. And the marked Lyapunov spectrum, it's when I need to look at the union of Lyapunov exponents. And for each periodic orbit, let me, this is, I could code them by a shift on D symbols. If you know the length spectrum, then you can actually recover the Lyapunov spectrum. So, no, it's in a different generality. Okay, so there are some old results by Delayave. And probably there are many other references which would say that if I take F and G to be my CR smooth expanding maps of degree D, and if I say that the marked Lyapunov spectrum of F is equal to marked Lyapunov spectrum of G, then F and G are CR minus epsilon conjugate. And by analogy with what I was talking about, I want to erase the word marked. And if I manage to erase the word marked in this situation, I will say some ideas of the proof. There is a hope that we could go to two-dimensional setting and we could replace the Lyapunov spectrum with the length spectrum and still proceed. Okay, now let me call Lyapunov spectrum F beta sparse if for any lambda and lambda prime which are inside of Lyapunov spectrum, what do I have? I have that lambda minus lambda prime, if there exists C positive such that this is less equal times lambda to the minus beta. So, so what does this condition mean? So it means that here's your real line, and on the real line you have this countably many points, which is your Lyapunov spectrum. So what you are afraid of? You are afraid of that you may have lambda prime and lambda which are extremely close to each other, And why is it a danger? You see, the reason these methods work is because of marking, but if two lambdas are very close to each other, you can mess up the marking. And if you mess up the marking, then you may expect troubles. And this condition of sparsity you could also see in the paper of Jakobson and Dolgopyat, where they give example of geodesic flows on surfaces of negative curvature, where you need to replace Lyapunov spectrum with the length spectrum. Okay, here's the main result. So the main result says that there is some critical smoothness. I use R, yeah. We did not calculate it. It's probably something like 10 or 20. Then there exists beta, which is positive, such that if F and G are C are close, Lyapunov isospectral, which means that Lyapunov spectrum of F is equal to Lyapunov spectrum of G, of degree 2, then F and G are CR minus epsilon conjugate. So this is the main result. And so I actually hope to express an idea which I don't think was used.
We need some sparseness in the assumption.
Yes. Beta sparse. Yeah, thank you. So now let me do the following. So as R goes to infinity, beta goes to infinity. The Layava, if marked length spectra, marked Lyapunov spectra coincide, then they are CR minus epsilon conjugate. So the problem is that once you say that F and G are close, you could make sure that the first, say, 100 periodic orbits have the same Lyapunov spectrum. But beyond 100, you have no idea. And I would like to draw some analogy with the KAM scheme, because it turns out, for those who haven't heard it, there is a Kolmogorov-Arnold-Moser theory. It's a theory where you are trying to find some good coordinate change which would conjugate some systems. And the problem which is faced in that theory is loss of regularity. So let me first state something which doesn't look related at the first glance. And this is one-dimensional Whitney extension theorem. And before I'll state Whitney extension theorem, let me introduce some objects. So suppose I have a map from a circle into a line. So I have a function on a circle. And I want to define so-called divided differences. So what is a divided difference? It's a discrete type of a derivative. And you could define this discrete type of a derivative for all orders. So you could think that this is first order discrete derivative, that is a second order discrete derivative, and so on. And the classical Whitney extension theorem has the following question. Suppose S is a finite set. And if S is a finite set, so if this is my circle, and this is my finite set, so the question is whether you could extend, if you extend your function, this is your function, so this is the value of your function h. So the question is whether you could extend your function h, knowing it on a finite set, to an infinite set, or to the whole of the circle. And in one dimension, the result is really sharp. So the result is the following. You have a finite set. You have a positive integer. Then there exists a bigger than 0 and an extension h to the whole circle, such that h coincides with the little h on the whole finite set. And if you look at the CR norm of your map, then it's less or equals than a times maximum of the m's divided difference of your h on S. So I don't know if the statement is clear. So the statement says that if I'll give you a finite set of points on the circle, and then I start forming discrete derivatives. And I form discrete derivatives of first order, second order, and so on, mth order. And then I take a maximum of all possible discrete derivatives. Then it turns out that there is an extension to the whole line, to the whole circle, which spoils the CR norm only by a fixed factor. And one thing which I think is probably a new idea in dynamical system is that when we will be doing, we will be looking for our coordinate changes in an inductive scheme. We're not going to do either localized perturbations or solving some homological equations. What we are going to do, we are going to look at the values of a potential coordinate change on a discrete set, and then Whitney extension will give us the coordinate change.
Sorry, what is M here?
M is, oh sorry, it's
R?
yeah, it's R. Yeah, it's R. R is some fixed number. Now, let me tell you what is the scheme of the proof, and let me tell you where is the loss of derivative, and what do we need to fight with. So now let me tell you about the method of proof. So what do we have? And let me, for simplicity, assume that the second map is linear. Okay, so then I have map G, which is just a linear expanding map, and I start with the map F, which is CR closed. So the game is going to be the following. So let me do a basis of induction. Let me look at the periodic orbits of some period k of my map. And in the case of a linear map, it's very easy to calculate them. They just equispaced collection of points. Then the basis of induction is to pick a map H, which takes periodic orbits of some period k naught of f into periodic orbits of some period k naught of g. Yes?
You are taking the linear map, so the hypotheses are trivial.
I understand, but I will. I could remove it later. I want to show you a rescaled picture, and after you'll see a rescaled picture, you will see that this assumption is not needed. It's just this has an explicit formula. If I remove it, you will not have an explicit formula, but I will show you a little window which I will zoom in, and I will say in this little window I need to do bounded distortion, and then I'll say, look, this window makes sense even without linear assumption. Okay, just to make understanding a little clearer. So what is my first step? My first step is I have f and g, and I adjust a little bit my map. And the way I adjust it, I hope it's visible. Now periodic orbits of this guy will coincide with the periodic orbits of that guy. Okay? You might want to keep in mind that it's linear, or might not want to keep it in mind. So I just want to make a first change of coordinates and say periodic orbits of period 1000 match. And if you want a slightly different picture, then a slightly different picture would be after a change of coordinates, the linear one is g, and the non-linear one is f, and what I have a match on all periodic orbits. So what is kind of the natural idea? The natural idea is to keep changing coordinates and try to match periodic orbits of an increasing periods. So let me try to at least naively do one step. So inductive step. And for inductive step, I hope it helps. So for inductive step, I have one periodic orbit of period k. I have the next periodic orbit of period k. If you don't want to keep in mind the precise formula, just forget about it. So this is for the map G. And then here's my map Fk. And there is a match of periodic orbits for map F sub k. So this is my inductive assumption. By inductive assumption, I have that there is a match of these two periodic points, and these are adjacent periodic points. Okay? And what would be my inductive step? My inductive step is to find hk plus 1. And what hk plus 1 will do, it will map periodic orbits of period k plus 1 of f into periodic orbit of period k plus 1 for g. So what does it mean? It means that somewhere here there is a period k plus 1 orbit. There is another period k plus 1 orbit. And these are the number of periodic orbits doubled, which means, and this is why in this section it's easier to see it. The number of periodic orbits doubled when you go from period k to period k plus 1. So in each interval of adjacent periodic orbits of period k, there will be two periodic orbits of period k plus 1. And this is a linear version, and that is a non-linear version. And for the non-linear version, what I would like to do, I would like to find h, which is going to map periodic orbits of period k plus 1 into periodic orbits of period k plus 1. And when you start looking at these formulas, you start to see that actually it seems a lot easier to use Wheaton extensions than to try to use localized perturbations, because the standard technique would be to use localized perturbations. And one other thing which I want to point out is that usually when you do localized perturbations, there is a gluing problem. Here, there is no gluing problem. You just calculate these discrete derivatives, and if you manage to get a boot bound on discrete derivatives, then you hope that you will get a good extension. So what is the plan? The plan is to adjust periodic orbits of period k plus 1 and define fk plus 1 to be hk plus 1 fk hk plus 1 inverse. And if I define it this way, then you'll see that period k plus 1 orbits of fk plus 1 is equal to period k plus 1 orbits of G. Right? So my coordinate change, it first fixed periodic orbits of period k, and then at the next step, it just adjusted periodic orbits of period k plus 1. And I hope it's visible that as k goes to infinity, periodic orbits get denser and denser. And if you can control the limit, then in the limit you will get a full coincidence. So certainly when you go well in this process, you need to find you want to find hk plus 1. And the first question is, how do you want to find h plus 1? And if you follow the classical recipe, that in order to find h plus 1, people use quantitative Lifshitz theorem. And so why quantitative Lifshitz? If quantitative Lifshitz theorem says that suppose you have you look, for example, at Lyapunov exponents of f, and you look at the Lyapunov exponents of g, and then if you look at the, for example, at ratio of derivatives of f and g along your periodic orbits, then if product of the ratios is 1, then you are supposed to get a co-boundary. But in our case, the word quantitative stands that suppose you have matching of Lyapunov exponents up to a certain high period. And then it turns out, and I did try, and I know that other people also tried, so if you just try the standard technology, then you lose derivatives. Which means that if you started with something which is CR, and if you do quantitative Lifshitz, then you will see that actually hk plus 1 has less regularity. And this is exactly what happens in KAM theory. You want to change coordinates, and when you change coordinates, you lose regularity. And what happens in our case is we say, okay, if we use quantitative Lifshitz theorem, we are losing regularity. Instead of using quantitative Lifshitz theorem, we take Whitney extension theorem, and very carefully we analyze this picture. I think this picture may be a little bit misleadingly simple. And the reason it's misleadingly simple because k is a very large number, and this is a periodic orbit of period k, and that is a periodic orbit of period k plus 1, which means that if you want to find out the location of, or the size of this interval, you need to iterate your nonlinear map k times, or k times and then one more time. So as a result, what you need to do, you need to get fairly sharp estimates on what happens on this interval. And well, actually, it's a good picture. You see, if Lyapunov exponents are different, then to the first order, you would say that this is lambda to the k, where lambda is a Lyapunov exponent, right? But if lambda of this periodic point is differs from lambda of that periodic point, you will start to see that the ratios are not close to 1, right? So you take this picture, you need to iterate it k times, and roughly speaking, after k iterates, this little distance grows to a size 1, which means that this is supposed to be your Lyapunov exponent to the power k. So on this picture, if this Lyapunov exponent and that Lyapunov exponent mismatch, you will start to see a mismatch in the corresponding distances. But actually, if you want to do CR estimates, you need to go to higher orders. You need to see that it's not only to the order lambda to the k, it is staying the same. It stays the same after that. Let's see, what time did I start?
5 minutes. You have 5 minutes.
I have 5 minutes. Yes.
The HK are just a hyperbolic continuation of the periodic point of period k.
So HK is an adjustment of period k points. So I take periodic points of period k of one map, and I move them to match with the other map. With the other map. So after this map, so the inductive assumption is that periodic orbits of period k match, and at the next step, I want to adjust periodic orbits of period k plus 1, so periodic orbits of period k plus 1 match. So if I can arrange the induction where at each step I adjust periodic orbits of first period k, they match, then of period k plus 1, they match, then of period k plus 2, they match. If I can control the norms, then in the limit, periodic orbits are going to be dense. Right? And so the kind of the technical part is that we need to control these divided differences. And in one-dimensional setting, it's enough to look at divided differences of neighbors only, which means that we first compute the first order divided difference here, then we take the adjacent integral, we look at the divided difference for a triple, and so on. And you may think that if you take a linear chart on the bottom picture, then basically we are looking at the distortion of a linear chart, which is here, with a non-linear chart. And so, or coordinate change, which brings you to a linear chart. And so what is quite interesting is for a long time we were stuck and we did not see what is the abstraction, and it turns out that there is an abstraction. So at a certain level, Whitney extension theorem is effective, but for a long time we did not see an additional cancellation so that Whitney extensions start to work. What does it mean? It starts to work. It means that the CR norms of the next age should be considerably closer to identity than the previous ones. And I mean, it will take time to explain what kind of abstraction we faced, but basically it is not it's not straightforward to see that the CR norms of these adjustments they behave nicely. And at this moment it is certainly a speculation, but if you have Anosov, you could look at some one periodic orbit, two-dimensional Anosov, one periodic orbit of period k. You could look another periodic orbit of period k. You look at the stable manifold, you look at the unstable manifold, and once we finish writing, it's getting close to be done. We will try to take two-dimensional map picture for nonlinear Anosov and try to apply Whitney extension to a linear Anosov, and hopefully the method could work. So we hope that there is a renormalization picture, which looks quite simple in dimension 1. We hope that there will be a similar picture in dimension 2. So maybe I'll stop here.
Thank you, Vadim. Any comments or questions? Rick?
Yeah, Kostya told me that it's pretty straightforward. I think it's an exercise for a graduate student. Yeah.
And if you assume instead of the also, you start with expanding a triangle. So the solenoid.
I don't know. You see,
much easier.
2D Whitney extension is a hell. I mean,
But
you
you
need
have
to.
a one-dimensional reduction.
If there is a one-dimensional reduction, it
No, it's the
may work.
solenoid is have the one-dimensional reduction, and you have a smoothness of the foliation, and maybe the Japanese pony imply that.
Okay, there is an explicit condition on a divided difference which needs to be satisfied. You take your nonlinear system, let's call it a nonlinear one. You test this divided difference. If it satisfies this key estimate, then the method works. So basically, procedure converges if a certain ratio is less than 1. In our case, it's less than, say, 0.9 to the power k. If it's exponentially small, the method works. And so. Analytic case. We did not try to do, I don't remember seeing in the literature analytic Whitney extension, because I guess once you have an accumulation point, it's almost an empty. Maybe you could do old dirty trick. You just approximate analytic with a smooth. You do the smooth construction, and then you look at the speed of approximation. So I'm not sure about this part. I believe it would work, but I'm not sure about this part. So you see, when I say CR controlled, I need to take R divided differences. When you say analytic, I probably need to let something go to infinity. Yeah? And at least now I'm not sure.
Do you have any examples of maps which satisfy the hypothesis of your theorem?
I didn't try to do it, but I'm 100% sure it works because I could take beta equal to 100. So it's any beta. It's just the price is that if you ask me, can you do it for C3? I don't know if I can do it for C3. If you ask me if I can do it for C300, then for C300 I can do it. And then beta is 100, and then you will have examples. But for some mysterious reasons, we need high smoothness.
So just one question. Your result is local. The rigidity is local. F and G should be sufficiently close. Why do you exactly?
Let me say. There are counterexamples to can you hear the shape of a drum. And in the case of Riemannian surfaces, they are done, roughly speaking, as follows. You cut your Riemannian surface into pence, and then you glue it differently, and it gives you a counterexample. As a result, a non-local statement, there is not much of a hope for non-local statement, because you could cut your pens differently, you could glue them, and you'll get a counterexample. These are famous works of Sonada and forget.
Is there any hope of local isometry for?
That's the dream. You saw it 3 levels.
Okay.
So, I mean, there is a Tal technique. There is some certain triple intersection property. Triple intersection goes to triple intersection. You could try to do it quantitatively. we first need to do a 2D case because Whitney extension becomes much more of a nightmare. But if you could do 2D conservative ANOSovs, then you could start looking at those pictures. But at the moment, I don't know. As geodesic flows, it should work. But then if it's an isometric, as flows, it should work. But as geodesic flows, there should be a triple intersection.
More comments or questions? If not, let's talk again.